name is Jakob Linskeseder. I work at Karriere.at, and today I'm going to be giving you an introduction to fuzzing. Like it's already been said, I'm a developer at Karriere.at, studying information security at FH Hagenberg, and I'm currently writing a dissertation on distributed fuzzing in Kubernetes. So, why am I talking about fuzzing? Why am I giving this talk today? The problem is, we as developers, we often write, writing good software is hard. So when I look at code I wrote 10 years ago, it was a big mess. It had a lot of issues. And even now, 10 years, with 10 years software developer experience, I still write code that contains bugs. And you can probably relate. I don't know a single developer that writes perfect code. Yeah, but there's a problem. Bad software can cause severe problems, especially if there is a hacker with bad intentions that is exploiting our bad software or vulnerabilities in our software. So one thing you can do is you can help this problem by improving the quality and security of a software. You can help this by starting to fuzz your software. But only few developers know about fuzzing. And so I hope I can tell you more today about what fuzzing is, how to fuzz an application, why you should fuzz, what and when you should fuzz. And we're also going to take a quick look at ClusterFuzz and OSS-Fuzz. So before we start, let's do a quick poll. Who of you knows what fuzzing is? Please raise your hands. OK, few people. OK, so some of you hopefully learned something new today. So when we start with fuzzing, the first thing we need is a target. What is a target? A target can be any piece of software. It can be a small Python script. It can be a JSON parser, or it can be a full-fledged browser. Typically, in your company, you will choose software you write in your company or you write yourself, because yeah, that's typically what you choose as a target. The next thing you need is a fuzzer. You can think of a fuzzer like a testing framework, like JUnit for Java or PHP unit or just for JavaScript. There are a lot of fuzzers, different fuzzers out there for different purposes, but they all work in a similar way. A fuzzer generates inputs and then sends those inputs to the target. And the goal is to send an input that will crash the target, our application. Because if we crash the target, we know there's a bug, and yeah, we want to fix those bugs. These inputs can be generated in different ways, different strategies to generate those inputs, and we'll talk about that later. So when the fuzzer sends an input to a target, for example, we send a JSON input to a JSON parser. The JSON parser says, OK, I parsed this JSON, and everything is OK. The fuzzer will think, OK, this input does not trigger a crash, and the fuzzer will continue with the next input. If the fuzzer finds an input that crashes the application and there is an exception, the fuzzer will typically generate a report with a reproducible test case. So we as developers can look at it and fix the bug. That's only a very basic overview of how fuzzing works. In reality, it will get a lot more complicated. So there are different approaches to discover bugs in software. Well, I'll talk about that before getting into more detail about fuzzing. So there's white box testing, black box testing, and gray box testing. White box testing means that source code is available. When we do white box testing, we can do code analysis, like static code analysis. We can do manual code reviews. And we can also do fuzzing, for example, with libfuzzer, which needs the source code to be available. Then there is black box testing. For a given input, only the output can be observed. What does this mean? For example, if we access a web application or an API via HTTP or remote, we can only see what gets back to us. This can be a 500 HTTP error code, this can be 200 status OK error code, but we don't know what's happening behind the API. This is also true for binaries, for example, for executables on Windows. Fuzzing is possible when we do black box testing, but it is very inefficient. Why is it inefficient? If you take a look at this picture, when we do black box fuzzing, what we probably would do, we would try to pick the lock of the gate that isn't even on the gate, and we will try to open the gate in a million different ways when we could just simply walk by. But since we are in a black box fuzzing test, we don't see that there's a way nearby. And that is when gray box testing will become interesting. Gray box testing is black box testing with additional insights. So what are additional insights? Additional insights tell the fuzzer or give the fuzzer more view into what is going on inside an application. This is also called instrumentation, when we instrument an application. An instrumentation can be added to an application by compiling the source code with a special compiler. This compiler then adds some special code, so the fuzzer will know what it is doing. Or we can run a precompiled binary in an emulated environment, and then we will also gain additional insights. This is a good target for coverage-guided fuzzers like AFL. So what are coverage-guided fuzzers? The goal of a coverage-guided fuzzer is to cover as much code as possible. If you're writing unit tests for your software, your goal is probably also to achieve 100% code coverage. So every single line of your source code is covered with a unit test. The same is true for coverage-guided fuzzers. You want to be in every part of the fuzzed application. You want to test every bit of it, every code path. Coverage-guided fuzzing is more efficient since new code paths can be more easily be detected, and then you can also go to these code paths and test new inputs. The only problems here when you have to pass a difficult if statement, for example. If your program reads an input and it only moves forward deeper into the program if you provide a magic string, there's a very low chance that the fuzzer will find this string and get deeper into the code. There's a lot of research going on this topic, and it will probably get a lot better in the future. So next thing we should talk about are fuzzing strategies. So how does a fuzzer generate its input it's sending to the target? There's the generation-based approach, where the input is generated randomly from scratch. So a generation-based fuzzer would typically start, if we are fuzzing a JSON parser, it would probably start with the number 0, then until number 9, then it would pick the string A to C, then it test all special characters, and so on and so on. This approach takes a lot of time, since the fuzzer has to build an input that is meaningful for our software. The mutation-based approach is more efficient. Here we have to provide an input as a starting point. If you're taking the example of the JSON parser, we could simply provide a JSON file. For example, a JSON file with some strings, some numbers, some arrays, some objects in it. and we provide this seed, like it's called, to the fuzzer, and the fuzzer will take this seed, mutate it, and then feed it to our software in order to cause bugs and crash it. Then there is the evolutionary approach, which uses feedback from the fuzzing target to learn the input format over time. For example, when we are fuzzing the JSON parser, the fuzzer will probably learn, if I use curly braces, I will get deeper into the code because this is a meaningful character for the JSON parser. Popular fuzzers using these two approaches, mutation-based and evolutionary approach, because they are the most efficient and they are the fastest. So popular fuzzers are, for example, American Fuzzy Lob. There's no typo, it really is like this, American Fuzzy Lob, or AFL. With AFL you can do white box testing and gray box testing. I will talk about AFL a bit later. And there's also libfuzzer, where you need the source code in order to compile it in a specific way, so you can test it. Other notable fuzzers I want to mention are HongFuzz, GoFuzz for the Go language, and there's also syscaller, which is a very successful fuzzer, kernel fuzzer, specially built for kernel fuzzing, since it already found a lot of bugs and security issues. And there are even more fuzzers, but I can't present them all now. So you probably ask yourself, how does a fuzzer look when it's in action? This is American Fuzzy Lob. This is what it looks like. At the lower left, you can see the fuzzing strategies the American Fuzzy Lob is using. It mutates the input we provided it to flip bits, to flip bytes, to do some arithmetics, and it also does trimming and other things. In this case, it fuzzes a PNG library. And we can also see the map coverage. So we can see 7.4% are already covered by the fuzzer. American Fuzzy Lob describes itself as security-oriented fuzzer that employs compile-time instrumentation and genetic algorithms to discover clean, interesting test cases. This may sound a bit complicated at first, at least it did for me, but it is easily explained. Compile-time instrumentation, as I already said, means that we have to compile our software in a specific way or run it in a specific environment so the fuzzer will know what the input it sends to the target will trigger it. If it finds a new code path, and if it does this input, it will create a crash, and it will get a little bit smarter this way. Genetic algorithms means that this fuzzer uses an evolutionary approach for fuzzing. So if we, for example, crash the JSON parser with a special character like I don't know, a white space, then American Fuzzy Lob will use this white space more often in order to produce more crashes. So American Fuzzy Lob is very popular because it is fast, it is pretty smart, and it finds real bugs. As we can see here in the next slide, these are only small extractions of software where American Fuzzy Lob found bugs. Some may have been security issues. This is mostly difficult to explain, to find out, because you would really have to test if a bug is exploitable. This is often a lot of work. But yeah, it found bugs in OpenSSL, Safari, Nginx, PHP, Tor, and LibreOffice, and a lot more. And when it comes to fuzzing quality, AFL, American Fuzzy Lob, is really good, because a good fuzzer is effective and efficient, because we want it to be fast and detect a lot of things. It should generate reproducible test cases, because we as developers, we want a test case, we can easily reproduce a bug, so we can fix it quickly. If we have to search through the code base to find the bug hours and hours, it would not be cool. And we want the fuzzer to have high code coverage, so we can test every bit of the software we are testing. We also don't want duplicate bugs because, yeah, that's time consuming, and so crashes should be duplicated. Okay, what fuzzing won't detect for us, this means detect. You have to consider that fuzzing won't detect access control bugs, for example, flawed business logic, poor architecture, and it also won't detect backdoors, because for a fuzzer, a backdoor is just like any other piece of code. It will fuzz the backdoor, but you won't know that the backdoor is there. So fuzzing is no replacement for manual testing. Please keep this in mind. So now that we have a solid base, we know what fuzzing is and how it works. I will tell you step by step how to fuzz an application. First thing, obviously, is to choose a suitable target. Like I said, typically this is a C or C++ program because they have the most vulnerabilities in them. Yeah, let's say we use a JSON parser, for example. The next thing we have to do is to choose a suitable fuzzer. There are a lot of fuzzers out there. You can mostly pick American Fuzzy Lob because it's a fuzzer you can use for a lot of different software. You can also use multiple fuzzers for the same software, but that's up to you. The next thing we need to do is to prepare the fuzz target. The fuzz target, our JSON parser. We have to compile it specifically. For example, if we are fuzzing with American Fuzzy Lob, we have to compile our fuzz target with a special compiler, so it adds the instrumentation to our target. The next thing we need to do is to prepare an input seed. So for our example, the JSON parser, we would just provide a JSON file, so it can has a good starting point. Then we run the fuzzer, and depending on how big our application is, this can take from minutes to hours to days to weeks. If the fuzzer finds a bug, it normally creates a report with a reproducible test case. And then there is the most important step, I think. You have to fix the bugs the fuzzer found. Don't underestimate this step. It will take some time to fix all those bugs. And sometimes they are also hard to reproduce, bugs that are hard to reproduce, especially if you find a bug because of a race condition, for example. Yeah. Now that I explained all these steps, you may ask yourself, whoa, that looks a little bit complicated. Why should I actually fuzz my software? First thing is, you find security issues. And you find it before someone else does find them. Because if you or your company provides an executable file or provides a download of an executable file, every other researcher or every other hacker can use this executable file and fuzz it to find software vulnerabilities in it. And so you should do this yourself to find them first. And as a nice side effect, you reduce exceptions and crashes in your software, so it will improve quality and stability. The next thing you probably ask is why, what and when should I fuzz? You should definitely fuzz if you're using a language with manual memory management like C or C++, because this language tends to have issues like stack overflows, buffer overflows, and so on. And you can detect those with fuzzing. You should definitely fuzz if your software runs on critical infrastructure like healthcare, aviation, finance, military, industrial control systems, and so on. And if your software passes untrusted data, you should also fuzz it. And this is true to practically every application that is exposed to the internet. So how can you fuzz your code apart from manual fuzzing? There is fuzzing as a service. There is Fuzzit, for example. It was founded, I think, 2 years ago, still a startup. And then there is Microsoft Security Risk Detection. You can use those, or you can integrate fuzzing in your continuous integration environment. If you have a small library you fuzz, you can do automated fuzzing, code push, for example. If you have a bigger software which takes a longer time to fuzz, it is probably better to do nightly or weekly fuzzing. I recommend you to check out those links if you really want to get started with fuzzing. It provides nice introductions and a lot of helpful links. And to get to the end of my presentation, I'm going to talk about ClusterFuzz and how it found so many bugs. ClusterFuzz is a product by Google and describes itself as a scalable fuzzing infrastructure that finds security and stability issues in software. This is not yet another fuzzer, but this is an infrastructure where fuzzers run in. For example, AFL, American Fuzzy Lob, will run in ClusterFuzz, or libfuzzer will run in ClusterFuzz. It is developed and used by Google to fuzz the Chrome browser and to provide computing power for OSS-Fuzz, which I'll talk about later. Just for example, the internal Google instance of ClusterFuzz runs on over 25,000 machines. So I think this shows nicely how important fuzzing is for Google, because they are investing so much computing power into fuzzing. So, yep, if Google is doing it, it can't be that bad. Then there is OSS-Fuzz by Google. It's a continuous and free fuzzing for open source software. You can think of it as a repository that just contains definitions on how to build and fuzz a project. So as an open source developer, I submit some configuration files. OSS-Fuzz will take these configuration files, build your software, and then fuzz it by putting it into ClusterFuzz. It supports C, C++, Rust, and Go. And there's a reward program by Google for integrating a new fuzz target. For example, if you're an open source developer of a bigger project, you can integrate your project into OSS-Fuzz, and you will even get rewarded by it. And what I really find astonishing is that OSS-Fuzz found over 14,000 bugs in over 200 open source projects since 2017. I think no developer could do this, achieve this, and yeah, so fuzzing really finds a lot of bugs. If you ask yourself what projects are in OSS-Fuzz, this is a short excerpt of projects. It's TensorFlow, Node.js, Firefox. You probably used some of this software. This is all getting fuzzed in OSS-Fuzz. So, coming to an end, what are the key points and takeaways for this talk? Fuzzing can help you and probably will help you to find and fix security issues. American Fuzzy Lob is a nice, popular fuzzer. You should try it out. Fuzzing helped Google to find over 16,000 bugs in Chrome. And I think that's pretty astonishing. And that's why I also think that you should start fuzzing your software. Thank you.
Thank you very much, Jakob. And we have time for some questions now. So we'll start off with this one. Most upvoted is, do you have any recommendations on integration of fuzzing into continuous integration pipelines?
Sadly not, no. I don't know if there are I suppose there are tutorials out there to integrate it in Jenkins or GitLab CI, but I haven't done so far. Because in my work, in my studies at the university, I practice on the scalability and doing distributed fuzzing, so I haven't touched this topic yet.
All right.
Sorry.
No problem. Can you, where's it gone? Okay, we'll go with the top one again now. How to apply fuzzing for a web application.
You can apply fuzzing for web application. It was really popular about 7 to 10 years ago because web apps, when web sites were then simpler, you didn't have that much Ajax and single-page applications. So yeah, today it is pretty difficult to effectively and efficiently fuzz a web application. So yeah.
Okay. Yeah, that answers it. Can you briefly explain how you would detect an exploit with the fuzzer?
Yeah. How do I explain this? As I said, for example, which example do I need? Do you remember Heartbleed, the bug that was there 4 years ago, OpenSSL issue? This OpenSSL library, someone should explain that someone later, after this bug was found, tried to fuzz this bug, and he was successful. So he took OpenSSL, he compiled it with a special compile flag so that memory, buffer overflows and stack overflows get detected. He then fuzzed it with American FuzzyLop and then got this crash. If you have a crash report by a fuzzer, you will then have to do manual work to really find out if this bug is exploitable or not. I'm not such a good reverse engineer, and I'm not so fluent in C and C++, so I cannot in detail explain how you would actually do this step from bug to security issue. So you have to have some knowledge for this to get an exploit chain done.
All right, thank you. I think the source code one we will leave, but I'm not sure if you have any.
I don't have my laptop here. Sorry.
Yeah, we can't show anything extra at the moment. Is it possible to use multiple virtual machines to fuzz in parallel to speed it up?
Yes, actually, ClusterFuzz is doing this, as far as I'm aware of. Yeah.
Okay, good. And let's do one more. Okay. Let's see. Is there one you would like to pick that you think you've got a good answer for?
Yeah, I can pick the first one.
The first one? Okay, so I'll read it out. Can you please explain how evolutionary fuzzing works? How is the feedback interpreted by the fuzzer?
I cannot explain it in detail, but I can try to explain it somewhat. For American FuzzyLop, if American FuzzyLop uses an input that triggers a new code path, so it gets into a new if clause, for example, then American FuzzyLop will detect and check what mutation of this input led to this new code path. And so it will use this mutation more often. And so after time, it will learn different interesting inputs it should use. There are a lot of interesting papers on this, so you should probably read them. It's pretty hard to explain, and there are a lot of different approaches on how you can do evolutionary fuzzing. There's an approach with AI, there's an approach with symbolic execution. So yeah, you should read papers on it. It's really, really interesting.
All right, thank you very much. And another round of applause, please, for Jakob.
Thank you.